Hey, welcome to the second video in our series on thinking mathematically. In this video, we're going to talk about comparing sizes of sets. And one of the concepts we're going to discuss at length is infinity. Infinity is a property of different sets that have an infinite number of members. And even though in the real world we might not encounter such sets, they're very useful in calculus and in other places to basically make calculations that otherwise would be very hard to do. So let's get started. Our first concept is to review sets. So sets are basically a mathematical construct that people use to denote a collection of things. Any kind of collection. It could be a collection of bananas, a collection of apples, or a collection of numbers. And when we talk about sets in math, they have the following properties. The order, first of all, doesn't matter. So if you have a set in a different order and you rearrange the elements, it's still the same set. Also, repetition doesn't matter. That means that if you have, for example, a set of 3 numbers, and then you have another set which you obtain by repeating the same number over and over, that repetition doesn't matter to us. We still regard it as the same set. So with this in mind, how do you define sets? One way to do it is to simply list all the elements in the set. And this works for finite sets, which we're going to talk about. But another way is to construct them out of variables. Now, if you recall, a variable like this means that n, remember, is all the natural numbers. That's 0, 1, 2, 3, 4, 5, and so forth. And this notation means n is a natural number. N is a variable that can stand for any member of this set. So n could be 5, 10, 20, billion, trillion, whatever you like. But it can't be -5. It can't be 1/2 because those are not in this set. So if you take all the possible natural numbers and then with each one you multiply it by 2 and add 1, this set is the odd numbers, right? So for example, if you have 0, n equals 0, then this would be 1. If n was 1, then this thing would be 3 because 2 times 1 plus 1 is 3. And then you get n is 3, then this one would be 7, and so forth. So you get 1, 3, 5, 7, 9. Basically, you get the odd numbers. This is how we were able to construct the set of odd numbers by just using a variable and referencing the natural numbers. So you can construct one set from another. And here's another example. Z is the set of all integers. If you recall, that means all the natural numbers, 0, 1, 2, 3, 4, 5, 6, 7, etc., and all the negative numbers they're negatives, like -1, -2, -3. So you get 0, 1, 2, 3, 4, 5, and also -1, -2, -3, -4, 5, but not 1/2, not 1/3 or -1/3. So what this says is let P, let's say, be the numerator, be any integer, and let Q be any natural number, where Q is not 0. And then you consider basically the set of all numbers P over Q, right? If you construct this set of P over Q, so you can get, let's say, -3 over 2. Or you can have 10 over 51, right? The set of all of these fractions is all the rational numbers. They're the numbers that you can express as a ratio of an integer to another integer, or an integer to a natural number. Okay, so basically 2 sets are equal when they have the same exact elements. That's when we say they're equal. So these 2 sets are equal because order doesn't matter, and these 2 sets are equal because repetition doesn't matter. That's the way it works. Let's talk about what a subset means. Subset is a simple concept. It's what you would normally expect. This is the notation. Now in math, we often want to have a very compact notation, so we're able to make manipulations and operations very easy. In this case, this here means A is a subset of B, right? A is a subset of B. What that means is that, remember, this is a variable, so any member of, let's say, whenever P is in A, any member of A is also a member of B. Or we could say P is in B whenever P is in A, right? So let's say A consists of apples, and this would also need to consist of apples, right? Because if something is in A, then it would also have to be in B. Now B could contain also other things. It could contain all the apples that are in A, but also contain bananas, right? Or it contains some other things. But it's got to contain everything. So here's an example. Here's a set of three numbers, 1, 2, 3, right? And obviously that's a subset of this one, 1, 2, 3, 4, 5. Why is it a subset? Because these 1, 2, 3 are found in here. All of them, with that exception, are found in here, so this is a subset. Now, if we say that A is a subset of B, and B is a subset of A, right? How could that be? Here we have this set is a subset of that one, but obviously this one is not a subset of that one. So how can they both be a subset of each other? That can only be if they're the same set, right? A set is a subset of itself. And so if both of these conditions are true, then we've got the same set. The other concept that comes up in mathematics is the concept of the empty set, or the set with no elements, right? This is useful because I can say, let's consider the set of all solutions to this problem. And then I do some work and I say, well, that's the empty set. Wait, so there are no solutions to this problem. It's unsolvable, right? That's one way to say it. Also, you could, if you are trying to be cute, you could say that this set is the set of concerns I give about this issue. And if it's the empty set, then that's a mathematical way of being funny. Also, the empty set is a subset of every other set. So this set over here, the empty set, we consider to be a subset because whenever something is in the empty set, it's also in here. Well, nothing's in the empty set, so by definition, as we say vacuously, it's true. It's true because this has nothing in it. Anyway, just remember about the empty set. It's basically a subset of any other set. It's one of its subsets. So let's review our sets of numbers. We're going to be talking about these sets of numbers because they're all infinite. You don't run out of these numbers. You can be counting them forever if you go one by one. And we're going to talk about what that means. But let's go over them really quickly. So n, once again, refers to all the natural numbers starting from 0. You know, that's our convention in this video. It's pretty widespread. 0, 1, 2, 3, 4, 5, etc., million, billion, trillion. Okay, but not 1/2, not fractions, not negative numbers. If you include all the negative whole numbers, then you get a set of all integers named z, because German mathematicians came up with these concepts of number sets of numbers, and z is the first letter of the German word for integer. So z is a set of all integers. Q is the set of all rational numbers. A Q is quotient, and again, German. So we've went over this already. I actually have one mistake here. I have that P is a natural number, Q is a natural number, but then that would mean that P over Q is positive. So this is actually, what I have here is a set of all positive rational numbers. It should have said P is an integer. So you could have negative rational numbers too. See how that works? So this n should have been a z. But this q is supposed to be the set of all possible fractions with an integer on the top and a natural number on the bottom. Now, it turns out that ancient Greeks figured out 2,500 years ago that some numbers cannot be expressed as a ratio of an integer and a natural number. One of those is a square root of 2. Another is pi or e. In fact, we're going to show just how many numbers there are that cannot be expressed in this way, and it could be a little mind-boggling. But it turns out that if you take all the rational numbers and then also all those numbers that can't be expressed as a rational number but still fit on the real number line, as we saw in the first video, that set is called R. You've probably seen it in all of your math courses in high school or any kind of primary school where you just have the number line, right? Including E, including pi. This is the real numbers. Finally, we've got complex numbers. If you recall, complex numbers include the real numbers. So A is a member of R. A is a real number. And B is a real number, but it's multiplied by I. I is the square root of 1. If that sounds strange, watch the first video. So I is the square root of 1, and you could do any algebraic operations with it. Adding, subtracting, multiplying, and dividing. You could do square roots. You could do all kinds of things, and this algebra works. And so the set of all those numbers is called C for complex. So using our subset notation, we know that every natural number is an integer, so n is a subset of z. Every integer is also a rational number, if I fix this here. So z is a subset of q. Q is a subset of r because, again, R by definition is all the rational numbers plus all the irrational numbers, so it contains all the members of Q. So Q is a subset of R. Finally, every real number is also a complex number. You simply have B equals 0, and then you have A plus 0, and A is real. So everything on the real number line, right, is also in the complex plane, the the two-dimensional plane. So basically, n is a subset of z, z is a subset of q, q is a subset of r, and r is a subset of c. And that will become important as we explore the sizes of these sets. And so far, we haven't even talked about what size of an infinite set means. Well, of course, it's infinite, but it turns out that there's much more to it than that. So here's where we could talk about that. And before we do, there's one more concept, and that is the concept of functions. You saw this in the first video, so I'm just going to review. Just like a set is a mathematical concept to basically express a collection of anything and have a series of operations you can do with them, like join two sets together. It's called a union. Okay. Here we have functions. So a function is an abstract concept also that we can use to represent any rule or machine or however complex that takes an input and gives an output. So we're going to use functions to represent a rule or a map that maps members of one set, like A over here, to another set called B. And this is the notation, F colon A right arrow B. It means that F takes members of A, and for some of them or all of them, it basically maps those members of A to B. In this video, we're going to say A maps all members of A to some members of B. And let's explore this. One way you can look at it is, here's A. It's a variable. Now, A comes from the set A. Small a comes from the set A. This thing is a variable, so it could stand for any member of this set. And so then you take A, you put it into the machine, F does something with it, and out comes B, right? Every time you put in A, F does the same thing, and you get the same B. In fact, you get only one of those B. So F can be thought of as a rule that, you put in an input and you get an output. And that's how we could kind of think about it with variables. So as you vary A, over here, vary this thing, as you take different members of A, you get maybe different members of B. Maybe the same ones. We're going to talk about that. So here are some more terms. A function maps members of its domain to its codomain. So look over here. Let A be a set of 3 apples. Here it is. That's the domain. And let B be a set of 4 bananas. So here we've got a set of apples and a set of bananas. Simple enough. And here we've got the notation. F maps every apple to a banana. So the bananas, the set of bananas is called the codomain. And the set of these 3 bananas over here is called the range. The range is a set of all outputs of F. Meaning, you see this banana is produced by applying F to this apple, right? This banana is produced by applying F to this apple. This banana is produced by applying F to this apple. But this banana is not in the range of F because there's no input that produces it, right? So the range could be either, it's a subset of the codomain. It could be smaller, or it could actually be the whole codomain, right? If the range is the whole codomain, that function has a special property which we're going to talk about. One more thing. This is probably obvious, but for each input that we give to F, there can be at most one output. Remember this? We put an input, right? And every time F is deterministic. It gives you, for the same input, it always gives you the same output. So there can only be at most one output. And you might have seen this in school called the vertical line test. So when F takes real numbers and gives you real numbers, you can graph F. And the graph that looks like this is not a graph of a function. Why not? Well, it fails the vertical line test. For this x, you've got 3 different distinct values of y. So given one x, like over here, this would be x, F gives you 3 different values of y. Well, that's not a function, because a function can only give you one output for every input. So now we've talked about sets and we've talked about functions. The functions take some member of a set and give you some member of the codomain, right? Now we're equipped to talk about the next concept, which is when a function maps the whole, so the range of the function is the whole codomain, we call the function onto. A function is called onto, you could say it 2 ways. Either the range is the whole codomain, okay? What that means is that every output has at least one input that produces it. See, this banana has an input that's here. That's apple produces this banana. This apple produces this banana. This apple produces this banana. But this banana has no output that produces it. Sorry, it has no input that produces it, right? So there's no apple that you can put into the function that will give you this banana. That's what this is saying. The above function is not onto, because one of the bananas is not in the range of F, right? The range is all the outputs, and this one is not. There's a banana in the codomain that's not one of the outputs. It's not in the range. So intuitively, you could just see a function maps the domain onto the codomain if there are no bananas left, if every banana is in the range, right? So for every banana, there is at least one input that will produce it. Now there's a flip side, a dual of this concept called one-to-one. A function has this property, one-to-one, if every output has at most one input that produces it. Once again, over here we had at least one input, right? This banana doesn't have a single input, so it's not onto. The function is not onto. Here, on the other hand, every output has at most one input that produces it. So this banana has no inputs that produce it, but that's okay because 0, the number of inputs, is less than 1. And we're just looking for at most 1. This banana has 1 apple that produces it. This banana has 1 apple that produces it. And this banana has 1 apple, right? It's also called the pre-image. Sometimes you put in this apple and you get this banana. So the above function is 1 to 1 because every banana in the range has exactly one input that produces it. Of course, if the banana is in the range, there's got to be at least one input, right, that produces it by definition, because the range is the set of all outputs. So for every output, there's got to be at least one input. But since this is 1 to 1, it's also at most one input. It's at least one input, and it's at most one input. That's why it's exactly one input, right? Well, if you've got exactly one input for every output, then you've got exactly every output for every input. We have a term for that. We say that the function, in that case, is invertible. When a function is both 1 to 1 and onto, has both those properties, right, then every output has exactly one input that produces it. Let's review why that is. If a function is onto, right, that means that every output has at least one input that produces it. At least one input. And if a function is 1 to 1, it means that every output has at most one input that produces it. So every output has at least one input that produces it. Every output has at most one input that produces it. That means every output has exactly one input that produces it. And then we can define an inverse function, which is notated thusly. The inverse function is a function that maps all the outputs back to their inputs because each output has exactly one input, right? So whereas over here, you've got, for example, this banana was produced by this apple. So now the inverse function maps the banana back to the apple. See, the arrows are reversed from before, essentially. Now, the domain of f is this, and the codomain of f is the bananas, but the inverse works the other way. The domain of the inverse f is the bananas, and the codomain, where the outputs are the apples. So the obvious relationship that you can think about is that the inverse of f maps things back to where they were before. That's represented by these double-sided arrows here. This thing is sometimes called a one-to-one correspondence between the apples and the bananas. Now don't get that confused with a one-to-one property of functions. Function is 1 to 1 if each banana has at most one apple that produces it, okay? But it's just called one-to-one correspondence, but we like to call it invertible function. It's the same thing. Here's what it means. You've got an apple, you apply f, you get a banana. And then you can apply the inverse of f and you get back the apple that you started with, right? Apple, banana, apple. Apple, banana, apple. Apple, banana, apple. Invertible functions are going to be very useful when we talk about the sizes of infinite sets. So for now, notice that for every a, if you apply f to it, you get a banana. Then you apply f inverse, right? You get back that input. See how concisely we can state this in mathematical terms, right? That's what this means. So, in fact, you see this f inverse, and then you apply f. It's kind of like multiplying these functions. It's called function composition. This open circle. You might have learned this in school. It means apply f first and then apply whatever's here. In this case, f inverse. So that would basically, they would cancel each other out. You get back the function, back to the input. That's called the identity function, I. It's just a function where you give it an input and it gives it back to you, right? I of 2 is 2. I of 3 is 3. I of -5 is -5. So that's what inverse does. It turns a function, if you compose it with the function, you get the identity. That's a little bit like in the first video when we had 1 over x, and then 1 divided by x, and then times x, you get back 1, right? And 1 is called the multiplicative identity. So that's why you have this notation, f to the -1st power. If you look at the first video, you'll see exactly why. x to the minus first power times x, right? That's the powers add. So you got minus 1, you got 1 here implied. Minus 1 plus 1 is 0. Anyway, so that's how inverse functions work. They kind of cancel out the function. Now, when you study this topic in school or you encounter it, sometimes people use different terminology than the one we've used here. I personally think that the terminology here is pretty clear, but just so you're aware, if a function is onto, some people call it surjective because it covers the whole codomain. And one-to-one functions are called injective because they're kind of injecting the apples one-to-one to the bananas. And the one that's invertible, they call bijective because it has both of these properties. But in this video, I'm going to use onto, function maps onto the whole codomain, one-to-one, right? Which means that every output has at most one input that produces it. And if it has both these properties, it's invertible, like we've been talking about. So we're going to use the concepts of sets and functions, which are both one-to-one and onto and invertible. We're going to use it to now talk about sizes of sets. What's the size of a set? Well, for many sets, we can just tell how many elements they have by just counting them, right? If you've got here a set of 3 apples, you go, well, that's the first apple, that's the second apple, and that's the third apple, and we're done. So there are 3 apples, right? That's how you would normally do it. But that only works for finite sets. What does that mean, finite set? If a set contains a number of elements, let's say m, then this is the notation we use. The size of A equals m. And m, we'll talk about it, has to be a natural number if the set is finite. So if a set B contains n elements and the set A contains m elements and n is greater than m, we say that the size of B is greater than the size of A, right? Like we went over here, we had A was 3 apples and B was 4 bananas. So the size of A is 3, and the size of B is 4. 4 is greater than 3, so there are more bananas than apples. Simple enough, right? But that only works for finite sets. A finite set contains n elements, where n is a variable. It's a natural number. It can contain 1,000,000 elements, 1,000,000,000, a trillion to the trillionth power elements, right? As long as that's a natural number, it's called a finite set. But in math, sometimes we deal with sets that are not finite. We call them infinite. And the set, obviously we can't count them. They don't have a natural number of elements, right? They don't have 1,000,000,000 or 1,000,000,000,000 elements. They have an infinite number. But we can still do a lot of things that help us compare the sizes of these infinite sets. We're going to use the functions and the invertible and onto and one-to-one properties in order to do that. So there are a couple ways you can compare the sizes of sets, both finite and infinite. Let's talk about how to do that with finite sets first. And then those same methods can be used for infinite sets. So to compare the size of a set, you basically want to say that one set is bigger than the other. For example, this set of bananas is bigger than this set of apples because there are simply more bananas here, right? So for finite sets, there's 2 ways to do it. The first way is, if I can find at least one function f that will map A onto B, okay, in this case the domain A is the bananas, and the codomain is the apples. If we map onto A, remember that means every apple is going to have at least one banana pointing to it, but maybe more. Then we say that the domain, the original set, in this case the bananas, is at least as big as the codomain, which is the apples, right? there's got to be at least as many bananas as the apples, because each function can have at most one output for each input, right? Each input can have at most one output, and we've covered all the outputs. The range is the whole codomain. So we've covered the whole codomain with this onto function, right? So it has to be at least as many bananas as apples. That's the point. So we say that the size of A, or the cardinality of A, is at least that of B, right? There are at least as many bananas as apples. How do we know? Because we can have an onto function. We can find one onto function, we're done. We know that there are at least as many bananas. Over here, look at this. Are there at least as many apples as bananas? No. And so you won't be able to find any function that maps A onto B. Because whatever way you map, there's always going to be at least one banana that's not in the range. The range will never be the whole codomain. Why not? Because for every input, you can have at most one output, right? And so there are simply less inputs than there are outputs. So here we know that the set of apples is smaller than the set of bananas. It's not at least as big, so it must be smaller. So that's how you can use onto functions. Okay, you can use onto, at least if you find that even one function that maps the bananas onto the apples, then you know that the set of bananas is at least as big, as numerous as this. And we say its cardinality is greater or equal to this, right? Okay. The second way is, again, the flip side. It's the one-to-one way. This is the first way used onto functions. The second way is going to use a one-to-one mapping. If we can find even one function that has this property, one-to-one, and it maps apples to bananas in this case. F maps this domain to these things, to this codomain, and it's one-to-one, which means, again, each banana has at most one apple that points to it. Then we say that the size of A is at most that of B, or cardinality of A is less than or equal to cardinality of B. So again, what that means, okay, is there are at most as many apples here as there are bananas. How do we know? How do we know? Because if there were more apples, let's say over here, here's a counter example, okay? There is no one-to-one function here that you can use to map the bananas onto the apples. There's simply more bananas. Any way you're going to map, you're going to have two bananas mapped to one apple. There's no way to have a one-to-one function like this, because there's simply too many bananas to cram into these three apples, right? So if you could have found a single one-to-one function from these bananas to the apples, you'd know that the bananas are at most as numerous as the apples. But since you can't, you know that the banana set is just bigger, and you got to cram it into these apples. There's going to be no way to do it one-to-one. It's also called, this thing is called the pigeonhole principle. You can Google it. Basically, the pigeonhole principle says, let's say you've got more pigeons than you've got these pigeonholes. So the pigeons will have to double up, right? To get all the pigeons into the pigeonholes, at least one of the holes is going to have two pigeons. Like you got these two pigeons over here kind of going into the same little nook and cranny. Okay, so to review, we've got these two ways to compare sizes of sets. The first one is if you can find an onto function. That means that the domain A is at least as big as the codomain B, if you could find an onto function. And if you can find a one-to-one function, then you know that the domain A is at most as big as the codomain. So if it's at least as big and at most as big, right, then it would be just as big. It would have the same number of elements, kind of the same size. And that, my friends, is how we're going to talk about infinite sets and sizes of infinite sets. Before we do that, I just want to give you one shortcut. So suppose that A is a subset of B. Suppose we had a set B, and then we decide to take a subset of it, like these two bananas here, and that's the set A. Well, if A is a subset of B, then the size of A is at most the size of B, right? Because that's, first of all, that just intuitively makes sense, but we could also prove it. All we have to do is find a one-to-one function that maps A onto B, or not onto, but maps A in a one-to-one manner into B. And a function like that is easily found, like the identity function, for example. You take the banana and you give it back. Take the banana and give it back, right? Maps everything to itself. That's a one-to-one function. It may not be onto, we don't know, but it's one-to-one, which already shows that the subset is always going to be at most as big as the original set, right? Because it's a subset. So if we know that A is a subset of B, and we want to show that A and B are the same size, we don't need to find a one-to-one function, because that's just the identity. We just need to find an onto function. We need to show that A is at least as big as B. By finding an onto function, right, where we just need to find a way to map this subset onto the larger original set to show they're the same size. So for finite sets, that can only happen if the subset is the set, the original set, right? Because if we omit even one element, then there's no way to map that onto the original set. But we'll find that for infinite sets, that's not necessarily the case. In fact, this pigeonhole principle over here, it only applies to finite sets. And we'll see that for infinite sets, it doesn't necessarily apply. So, remember how we said to find the size of a finite set, all we have to do is count the number of elements in that set, right? The number of members. Let's look at this intuition. Like, what's going on when we're counting them? So, if we can find an invertible function, right, that maps A to B, it maps A to B, then we know that this function is both one-to-one and onto, right? By definition, that's what we call invertible. So if it's one-to-one, that means that the size of A is at most the size of B. And since it's onto, the size of A is also at least the size of B, and therefore the size of A equals the size of B. So if we have a finite set, this is the same exact thing as actually counting the elements. What does that mean? Well, the act of counting these bananas over here, right, involves making an invertible function from the set 1, 2, 3 to the set of these bananas. So we say, this is the first banana. That's the second banana over here on the right. That's the third banana. See, by doing that, we counted the bananas. Whoop-de-doo. But yeah, that's basically the same as setting up this invertible function. You see, mathematics describes that situation in these abstract terms, and it applies here. So for finite sets, counting is just setting up this invertible function between a set of, let's say, these three numbers and these objects. So the reason this seems very obvious is because we've used mathematics to basically describe a very familiar situation. We've got finite sets of objects, like these bananas, and we've developed sort of ways to describe how to find out if two sets are the same size, right? Now, with all this, though, we're going to explore a new concept of infinite sets. See, some sets have an interesting property in mathematics of being infinite. What that means is they cannot be counted using any natural number. Suppose that I have here an infinite set of bananas. This ... indicates that the set of bananas has no end. What that means is that suppose I had a domain that I wanted to map onto these bananas, and the domain had exactly three objects, three numbers or whatever. If the size of the domain is natural number like 3, I won't be able to map the domain onto the bananas. forget invertible, I won't even have a function that's onto. Because, okay, here's the first banana, here's the second, here's the third. Okay, we've run out of numbers, but there are still more bananas left to go. That's what it means to be infinite. So no matter what domain you choose, if the size of the domain is some number, some natural number, like a million or a billion, it will still be too small. There's no way to map this finite set of numbers onto this infinite set. So basically, infinite sets are sets for which you can't have finite sets, which are size n, right, natural number. You can't map them onto the infinite set. Infinite sets may not even exist in the real world. You know, there's no infinite set of bananas that you've ever seen, right? And people wonder if there's an actual infinity in the real world. Let's say there's not, right? But as a mathematical concept, it makes sense. And it's very useful, as we will soon see. However, infinite sets defy intuition sometimes, because our intuition is based on things we've experienced, and we've built up certain things that we expect, certain properties that we expect. Infinite sets sometimes violate those expectations. And here's one example brought to you courtesy of Hilbert, a very famous mathematician who lived 100 years ago. He said, imagine a hotel with an infinite number of rooms. Remember, that means that if you start counting them, right, you'll never stop. No natural numbers can be used to count all of them. So imagine a hotel with an infinite number of rooms, and each room is already full, okay? Each room is full. It has a guest. Now a new guest arrives. Can they get a room? All the rooms are full. So it turns out that they can. With an infinite number of sets, you simply move the first guest to the second room. The second guest at the same time has to go to the third room. The third guest has to go to the fourth room, and so on. Since there's an infinite number of rooms, you never run out of rooms. And so each guest can be moved to the subsequent room, leaving the first room completely free for the new guest to come in and occupy that room. The end result, once again, we've got each room is full and has a guest, but somehow we can accommodate any finite number of guests in this way. Compare that to the pigeonhole principle that we've had a few slides before. Look over here. Suppose that we've had a situation where there were 9 rooms and 9 pigeons, right? And now a 10th pigeon comes. All the rooms are full. All the pigeonholes are full. Now this 10th pigeon has to double up with some other pigeon. There's just not enough pigeonholes because there was a finite number. There were 9. And now there's 10 pigeons. But over here, we've got an infinite number of rooms, an infinite number of guests. And now you can have 1 guest come, 2 guests, 3 guests, 1,000,000 guests, right? And they still can find room. Infinity plus 100 is still infinity. The same way you can take the guests out of the room, right, and move them this way. So infinity minus 100 is still infinity. You can have any finite number of guests, 1 billion, 1 trillion, to the trillionth power, right, and they would still fit. That's one way in which infinite sets defy our intuition. That's a simple way. There's actually a lot more complicated ways that you go, what? And you can look at other videos on YouTube. There's one actually by Vsauce. He talks about the Banach-Tarski paradox. If you Google for that, he can show how you can theoretically, using only theoretical math, sort of double a sphere into 2 spheres or 1,000,000 spheres, rearranging an infinite number of points. We're not going to talk about that in this video. Go watch that one if you want. Now, we're going to talk about, on the other hand, countable infinities and uncountable infinities. So to introduce that, we first have to introduce one more concept. It's just the word, sequence. An infinite sequence of numbers is actually just a function. It's a special case of a function where the domain is natural numbers. Okay? So natural numbers remember, are 0, 1, 2, 3, 4, 5, and so forth. And we map this to some infinite set, or maybe a finite set, doesn't matter. But as long as the domain of the function is natural numbers, we call the function an infinite sequence. Here's an infinite sequence. It's 1, 1/2, 1/4, 1/8, 1/16, 1/32, and so forth. So this sequence, as you can see, gets each number is half of the previous one. One way to notate it is as a function. Give me an n, and I'll give you an output. 2 to the n, and then reciprocal, right? 1 over 2 to the n. So this would be 1, 1/2, 1/4, 1/8. So it's a function that maps natural numbers to rational numbers. By the way, notice as n gets bigger, right, as you go to the right, the sequence approaches closer and closer to 0. It's like a song that fades out, at the end, but it never stops fading out. So like even after a million years, it's still playing, but it's like really, really, really faint. That, by the way, is the concept of calculus, which I'm going to talk about in another video. Calculus is a study of basically limits and sequences approaching things, and that's for another video. But what I want here is just for you to understand, if a function maps natural numbers to something, it's called a sequence. That's all. So a set is called countably infinite if you can cover it with a sequence. Mapping the natural numbers onto a set is like counting them. Think about it. Let's say you've got this infinite set of bananas, right? So I say this is the first banana, that's the second, that's the third, and I continue. That's the fourth, that's the fifth, and I never stop. If I can count all the bananas in this way so that every banana has at least one natural number that was used to give it an order or a place, that's the millionth banana, that's the billionth banana, right? Each banana at the end has been covered, just like the rooms were full in Hilbert's hotel, right? Then we say the function is onto, because every banana has at least one input that produces it. So mapping the natural numbers onto a set is like counting them. And if we can count all the numbers, we call that a countably infinite set. All we have to do is find the sequence from natural numbers to the bananas that is onto, and so every banana is found in the sequence somewhere. You get a banana, oh yeah, that's the millionth banana. Oh, this one, that's the billionth, trillionth banana. Oh, and that one is the third banana, right? So that here we've got a countably infinite set of bananas. We've got our sequence. Domain is n. Codomain is bananas. Of course, a countably infinite set, by the way, has to be infinite. So it's both infinite and you can map natural numbers onto it. Let's see if the set of integers now is countably infinite. We understand that all natural numbers are integers, right? But not all integers are natural numbers. -2 is not a natural number. -5 is not a natural number. So aren't there 2 times as many integers as natural numbers? Well, it turns out infinity times 2 is just infinity. A countable infinity times 2 is still countable. Here's how you can do it. It turns out the integers are countably infinite. If you just tried to count all the positive integers first, you'd never get around to counting the negative ones. Okay, so for example, I start 0, 1, 2, 3, 4, 5. But what about -1? I don't get around to it. But there's a smarter strategy. You can alternate positive, negative, like this. 0, 1, -1. 2, -2. 3, -3. At the end of that, all the integers have been counted, right? At some point, every integer, we're going to get to it. And we've never run out of the natural numbers. So we've been able to map the natural numbers onto the integers. Or, put another way, we've been able to make a sequence of integers that basically is onto. It covers all the integers. So in this way, the sequence maps the natural numbers onto all of the integers. So natural numbers are at least as big as the integers. But since natural numbers is a subset, and so they're at most as big as the integers, turns out that natural numbers and integers are sets of the same size. They're both infinite. They're both countably infinite. So here we have that a proper subset, basically natural numbers, every natural number is an integer, but not every integer is a natural number, and yet they're the same size. So this set is a superset, right? It's got elements that this one doesn't have. But yet you can make this one-to-one correspondence, this invertible function that's both onto and one-to-one. We've been able to use the concepts that we learned back here. We've been able to use these concepts on infinite sets, and we're just getting started. So we've been able to count the integers. Well, what about rational numbers? The next step up, right? The next superset. Rational numbers includes all natural numbers, all integers. It includes -5, -6, and it also includes all fractions, 2/3, -2/3, right? Turns out this set is countably infinite too. We just need a slightly smarter strategy. First, we're going to put all these fractions into an infinite grid. Okay? Here we have 0/1, let's say. And we're going to increase the denominator going down. So 0/2, 0/3. Obviously, that's the same number. But it doesn't matter if the sequence repeats. We just need the sequence to cover all the rational numbers to show that the natural numbers are at least as big as the rationals, and therefore the same size. So here we're going to make the numerator increase to the right, and here we're going to make the numerator decrease to the left. So we've basically covered all the rational numbers, right? Any integer over any natural number. So again, if our strategy was just to count them in one direction, that would be kind of stupid, because then we'd never get around to counting the rest. We just go to the right. However, if we did the following strategy, we'd count them all. Start with, let's say, this one. Doesn't matter, but let's say with this one. And then you count them in a triangle like this. And after you're done with that, you count them in a triangle like this, right? So that's the first one, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, and so forth. As you can see, these ever-expanding triangles, they cover this whole grid, right? Because there's nothing up here. But even if there was, you could have a strategy where you could do squares. The point is, you're able to count all the countably infinite rational numbers. So we construct a sequence that counts all the rational numbers at least once. So this time we show that the set of natural numbers is at least as big as Q, but since it's a subset, it's also at most as big as Q, and therefore the size of natural numbers is the size of the rational numbers. Wow. They have the same size. 1, 2, 3, 4, 5 has the same size as all fractions. Okay. Let's take this a little further. If A and B are countably infinite, like the integers or like the rational number set, their union is also countably infinite. If you put those together, let's say I've got a countably infinite set of chairs and a countably infinite set of tables, right? If I now put them together, I can count those as well. I just take the first chair and then the first table, the second chair and then the second table, the third chair and then the third table, alternating like we did with the integers. And in this way I can basically count the combined set of all chairs and tables. In fact, I could have 10 countable sets, put them together, say chairs, tables, and koalas, right? And that would still be countable. I could have 20, 30, 50. In fact, I could have a countable number of countable sets and put them all together, and the result would still be countable. You can arrange them in a grid the same way that we did with Q. So here remember, this is a countably infinite number of things just in this row. Here's another row of countably infinite things. And there's a countably infinite number of rows. And you can count the whole grid. So if that's the case, we might suspect maybe every infinite set is countable. I mean, you put together even an infinitely countable number of infinite sets and the result is still countable. So are all infinities countable? Turns out no. The next step up, the real numbers, they're uncountable. That literally means that you cannot construct a sequence of real numbers that will list all the real numbers. And we'll show that here. Another way to say this, by the way, in mathematics, we want to have symbols about things we talk about frequently. So it turns out that the set of natural numbers, integers, and rational numbers are all the same size. And we call that aleph 0 or aleph null. Aleph is the first letter of the Hebrew alphabet. And aleph null is the smallest size of infinity. It's the countable infinity. So it turns out that the real number, the size of real numbers is bigger than aleph null. They're not countable. We can't, so here's the proof. We won't be able to list all the real numbers. To prove that, we'll try to list the real numbers just in this interval. And if we can't list even those, right, then certainly the real number set, which is bigger, is therefore has bigger size. Okay, so suppose we could. Suppose that we had a sequence of real numbers in this interval. So each of those real numbers has a decimal expansion. That's how we can define real numbers, by the way. It's the set of all numbers with some kind of decimal expansion, right? So each of these numbers has a decimal expansion. And let's say we were able to list them like this, a countable way. So we have a countable list. This is the first number, second number, and so forth, forever. It turns out we can construct a number that's not on the list. Given any list, given any sequence of these numbers, we can easily construct a number which is also in this interval, but which is not in the sequence. The way we do that is by making that number different by one digit from each of the numbers in the list. So take the first number and make the first decimal place different. Let's say it's 0, so we're going to make it a 1. It's a 2, so we're going to make it a 3. Here's another, let's make it different from this number by making this 2 a 3. This 3 will, so it's a 3, so we'll make a 4. And so forth, right? This is called Cantor's diagonal argument, named after Georg Cantor, also German name, German mathematician. He basically invented the idea of sizes of sets. And so this is called Cantor's diagonal argument. Once you construct this number, it is different than each of these numbers because at least one digit is different, right, in the same place. So this number is not on the list. This number is nowhere to be found in this list. So this sequence did not list out all the real numbers, even in this interval. This shows you can't list all the real numbers. There's actually more real numbers than you can list. And that means that the size of real numbers is bigger. It's the same concept that we had all the way back here, where we said, if you cannot find an onto function, right? You cannot find a function mapping all these apples to all these bananas. There's simply not a function out there that can cover all these bananas. It means that their number of bananas is simply, that set is more numerous. There's simply more bananas than there are apples. That was in the finite world, and for the first time we see that in the infinite world. So there are levels of infinity. The real numbers are simply more numerous. So if the countable infinity is called aleph null, the next level of infinity we call aleph 1. The real numbers, the size of real numbers is called C. Now you may think, maybe C is Aleph 1. It's the next level, right? Well, we're not sure. And it turns out in mathematics, we can't prove one way or the other using the set of axioms in set theory that we have. If you want to understand more about what I just said here, Google Zermelo-Fraenkel axiom. And it's a set of axioms or things that we use, that we can manipulate as being true, and we can use those statements. So in mathematics, it turns out we don't know if the real numbers are the next level of infinity or if there's some level in between. But in any case, the real numbers, the real number line, that level of infinity is called continuum. So you can think of continuum as the number of points on a line, a continuous line, versus a bunch of countable points like 1, 2, 3, and the fractions. You can kind of feel those points, those sets being constructed from individual points. And here, it's like, boom, we draw with a pen, like a continuous line. That continuum has more points than all those countable sets. So yeah, this is like a special font. It's a fancy C, but it's used normally. It's a font called Fraktur. Anyway, so what is the cardinality of the next set up? The complex numbers. Is it bigger than R or is it equal to R? Meaning, R is like a one-dimensional line, right? That's the continuum. And C is like a two-dimensional plane. The set of complex numbers, if you saw the first video, can be put on a plane. It can, all the possible complex numbers correspond to a point in the plane, and all the possible real numbers correspond to a point in a line. So it turns out that there are functions that can map a one-dimensional line on a two-dimensional plane, onto a two-dimensional plane, meaning every point in the plane will be in the range of this, of this function. In fact, the function could be a continuous curve like this. This sequence of continuous curves that you see here, as you can see, it gets more and more dense, right? Each of the points in this two-dimensional two-dimensional plane eventually is either on the curve or really, really close to the curve, right? And if you study calculus, in another video, I'll show you, I won't prove it here, but it turns out that in the limit, the function is also a curve. It's a continuous curve in the limit, and it actually covers every single point in this square. You can actually map this one-dimensional thin line, infinitely thin line, that eventually it gets more and more complex and has twists and turns. Eventually, it actually covers the whole square. This kind of curve is called a space-filling curve, and it shows that the size of R equals the size of C, because you can make a function like this space-filling curve that fills up all the space. It maps R onto C. Wow. This is another counterintuitive example of infinite sets. You can imagine a small line, and you can just twist it around, and it can fill a square. It could also fill a cube. You could have it fill a room, okay? If we talk about, in topology, 10 dimensions, 20 dimensions, it could fill those too. So it turns out that basically, if we go back all the way to the beginning, and we talk about our sets, then we have n, z, and q be the countable infinities. And then we jump and we have the continuum. We have real numbers and complex numbers, which are just a larger infinity. Having established all this, we're left with just a couple more questions. The first is, how many irrational numbers are there? In other words, if the real numbers are uncountable and the rational numbers are countable, then what is the size of real numbers minus all the rational numbers? Well, to answer that, let's think of a more familiar scenario. What if we had an infinite set and we removed 999 elements from this set? the result would still be an infinite set. We can show this because if the result was a finite set, it would have had n elements, where n is a natural number. And that would mean that the original set had n plus 999 elements, which would mean that it's finite also. But we initially supposed it was infinite. It's a contradiction. So that means if you remove any finite number of elements from an infinite set, you're still left with an infinite set. Infinity minus 1,000 is still infinity. So the same way, in the same manner, what if we took all the real numbers, r, which is uncountable, and we removed all the rational numbers, leaving only the irrationals, right? So again, if it turns out that the set you're left with is uncountable. In other words, r is uncountable, and then you remove a countable number, you're still left with an uncountable infinity. Again, we can show this the following way. Suppose that you're left with a countable infinity. Suppose that there were countably many irrational numbers. Well, r consists of the rationals and the irrationals. And we've shown that the union of two countable sets is countable. So r, which we know is uncountable, which would have been shown to be countable, which is contradiction. Meaning that if r is uncountable and the rational numbers can be counted, then whatever's left over must also be uncountable. There are literally an uncountable number of irrational numbers. There's literally more numbers that you cannot express as a ratio, as a fraction, than there are numbers you can. And I think that's kind of cool. So we found that the natural numbers is an infinite set, and it's larger than any finite set. And then we found that the real numbers is an even larger set. It's an infinite set that is literally larger. So there are countable infinities, and then there's the continuum, which is uncountable. So one may ask, basically, is that it? Is the continuum the largest infinity you can have? Or maybe you can have even larger infinities. The question is, and this is the last question we're going to ask in this video, can there be a largest infinity, a set that there is no larger infinite set? So to answer this, we're going to introduce one last concept, and that concept is called the power set. Although I marked this concept as advanced, it's actually pretty simple to explain using the stuff we already know. So given a set A, any set A, the collection of all its subsets is called the power set of A. So for example, if this is a set A, it consists of 3 numbers, 1, 2, and 5, then what possible subsets could you have? Well, first of all, you could have the empty set. If you remember, the empty set is the set with no elements, and given any set, right, any set, it's a subset. So the set with no elements, then we've got the set with just the element 1, then we have just with 2, and just with 5, right? So much for the sets with 1 element. How about subsets with 2 elements? We've got subset 1 and 2, we've got 1 and 5, and we've got 2 and 5. Remember, the order doesn't matter, and repeating the same element doesn't change. So much for the set of the subsets with 2 elements. Now, what about subsets of 3 elements? There's only one. There's the set itself, right? Count them all together. You got 1, 2, 3, 4, 5, 6, 7, 8. 8 elements. The power set, as you can see, is a bigger set. It's far bigger than A. A had 3 elements, and all the possible subsets, there are 8 of them. When A is a finite set, that is, the size of A is n, then in fact the size of the power set is 2 to the power n. That's why you have this notation. This is the power set, and this is mathematical notation. It says it's the set of all B, where B is a subset of A, right? Very compact. So 2 to the A is called the power set. of A. And it's far bigger. If you want to see, by the way, why this is, that the size of 2 to the A, like for example, A has 3 elements and this has 8 elements. If A had 4, then this would have 16. If A had 5 elements, this would have 32. Well, here's why. Because each subset of A contains some of the members of A, right? Just like we have here. And let's take this variable. Any of these members, 1, 2, and 5, could either be in a subset, like it is here, or not be in a subset. For example, the subset doesn't have 2, but it has 5, right? So that's 2 possibilities per element. Each element could either be in the subset or not be in the subset, right? And since there are 3 elements, that would mean there's 2 possibilities times 2 times 2. That's 8 possibilities. So that's why if a set has n elements, that's a total of 2 to the n different subsets representing 2 to the n possibilities. So for example, the empty set, none of these, right, are in there. So it's like false, false, false. And in this one, true, true, true. They're all in there. So yeah, this one is like true, false, true. So that's why there's 2 to the n possibilities. And that's why the power set is far bigger and the size grows exponentially with the size of the set. But what if A is infinite? What about an infinite set A? We can show, in fact, that its power set is always bigger cardinality. In other words, you cannot map A onto its power set, but you can map its power set onto A. All you'd have to do to map the power set onto A and cover all the elements of A is just, look, the power set has 1 by itself, right? 2 by itself, 5 by itself, right? So you just map those subsets to the elements, right? So the subset, this one maps to the 1, this one maps to the 2, this one maps to the 5. Whoop, you covered the whole thing, right? As for these other ones, you can map them anywhere you like, including the empty set. Doesn't matter because you've already mapped the power set onto the set A. But the other way, you can show that you cannot map A onto the power set. There's just not enough elements to cover the whole power set. And if you want to see the proof, then simply pause this video and the proof is right here. But it's an advanced proof, so I'm not going to verbally go through it and confuse everybody who just doesn't care and just accepts this as a fact. So what does this fact imply? It means there is no biggest infinity in mathematics. There is no biggest infinite set, because given any set, its power set would have an even bigger cardinality. So in mathematics, we denote the sizes of infinities, like I said, as aleph null or aleph 0, and then it becomes aleph 1, aleph 2, and so forth. This is the next largest infinity, the next largest infinity. And we've also got these numbers, which is bet, the second letter of the Hebrew alphabet. Bet null, bet 1, bet 2, bet 3. All these numbers are called cardinal numbers in mathematics because they're used to talk about sizes of infinity. In fact, it turns out that aleph null and bet null are the same by definition. They're both the size of the countable infinities, which is the smallest infinity. But then it's an open question in mathematics, and we can't actually know whether the next infinity, aleph null, is the continuum. You see, the way you obtain bet 1, bet 2, bet 3 is like this. Start with countable infinity, and then you take its power set. And it can be shown that the real numbers, the continuum, has the same size as the power set of natural numbers. You could sort of see that if you take a binary expansion of a real number, 0, 1, 0, 1, 0, 1, that's kind of like the power set. So then you take the power set of the real numbers, and you get a vastly larger set. You get a power set of that, you get a vastly larger set, right? Using the power set operation, we have these bet numbers that just keep increasing. There's no larger infinity. The question in mathematics, and this is called the continuum hypothesis, of whether bet 1 equals aleph 1, meaning, is the continuum the next largest infinity? Or is aleph 1 somewhere over here? Is there some kind of infinity that's between countable and continuum? That's the continuum hypothesis, that they're equal. The generalized continuum hypothesis is that bet 2 is equal to aleph 2, bet 3 is equal to aleph 3, and so forth, meaning that in order to get the very next level of infinity, you have to use the power set operation, and there's nothing in between. So hopefully, if you followed me this far, you know quite a bit more about infinity and infinite sets than you did before. And that's a large part of mathematics. So what have we learned in this video? In this topic, we've explored the concept of infinity through considering functions on infinite sets. We took concepts like the size of a set, which are easy and familiar when you apply them to finite sets, and we worked out what it would mean for infinite sets. And the resulting generalized concept is called cardinality. We also explored useful properties of functions that enable us to map one set onto another, the onto and the one-to-one. And interestingly, it turned out that some infinite sets are the same size as their proper subsets. So the infinite sets integers, for example, and rational numbers are the same size as the set of all natural numbers, even though they contain this set and much more. But since you can count all of their elements and never run out of natural numbers, if you can make a sequence that covers the whole set, that means that the natural numbers are at least as big. And since they're at least and as most as big, they're really the same size. There's a whole class of countably infinite sets, and their cardinality is denoted aleph null. On the other hand, when it comes to the real numbers and the complex numbers, these, we've shown, cannot be counted. There's no sequence that covers all of them because their cardinality is bigger. That cardinality is denoted C for continuum. It's also the same as this bet 1 can be shown. But this isn't the biggest cardinality either. Given any set, we can construct its power set, which has an even larger cardinality, and thus there is no biggest infinite set in mathematics. Cool? I think so. One last point. Before the 19th century, people just thought of infinite sets as being infinite. They didn't have a concept that some infinities are bigger than others. It was Georg Cantor that first, with his diagonal argument, showed that real numbers are uncountable and that there are actually levels of infinity. Since then, mathematicians have figured out all kinds of abstract ideas like transfinite numbers and other things like that. So if you're interested, all these topics, go ahead and study them. I really hope these videos have been helpful, and check out my other videos. If you like it, leave comments below and tell me what you think. I hope you're having a great day.